Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Stop on inside and you... Wait. Did he say Mr. Robinson? Mr. Robinson, it's too early for this. I'm trying to learn some math stuff here, and you're already getting other math stuff? Yes, that's right, kids. We are doing some Chapter 7 stuff on special quadrilaterals. We have parallelograms, rectangles, rhombuses, and squares. Among anything else that's quadrilateral-based, polygons as well are making a cameo appearance actually at the very beginning of this. Totally forgot about that. Section 7.1 to 7.4 of the Big Ideas Math Integrated Math 2 textbook. Now, I'm leaving out section 7.5. My students aren't particularly testing on that stuff. That is on trapezoids and kites. If I still make a video out of that stuff in the section of the textbook, I will do so, as well as its own Chapter 5 review in there, and the test and cumulative assessment if all goes swimmingly. So, check out the description section below for the PDF that we're going to do here, where this is another packet. I did one out of Chapter 6 titled, Are You Ready? It's something made from a colleague of mine, and so is this one as well. So, let's figure out how this thing looks. And this packet is no slouch, by the way. It is 10 pages long. Guys, are you ready? Let's go ahead and take a look at this. Grab your calculator, grab your brain. I want to get started. And I want to mostly talk through my work in teaching. Otherwise, I want to mostly do the problems. A little bit more drill and kill. Saturday night. I want to do Saturday night stuff. All right, let's go ahead and get started. Number 1, letter A, or part A, solve for x. This is a polygon of 4 sides, otherwise known as a quadrilateral. Now, if you didn't know that its interior angle sum is 360 degrees, you'd want to calculate that somehow. I use the letter D for degree sum here, and you multiply 180 times the number of sides or angles you have minus 2 to get this determination. It's 180 times n minus 2 as an overall formula here. The number of triangles that are in the polygon, 1 triangle, 2 triangles, is derived from the n minus 2. The interior angle sum of a triangle is 180. 180 times 4 minus 2 is 180 times 2, which is 360. Now, that's not x. That is the interior angle sum, all 4 of these angles together. So when I add 4 of these angles together, I want to set it equal to 360, and then I will solve for dat x do. If it was 5 sides, it'd be 5 minus 2, and 20 sides, 20 minus 2, things like that. I should have got my calculator ready here. This is 236 plus 50 is 294. So x plus 294. And this looks like x equals 66. Okay. So there's problem number 1, solving for x. Problem number 2, solve for the measures of angle B and C. In this, also quadrilateral. Listen, we now know it's 360 degrees. Let's go ahead and use that as needed. Now, solving for x takes all 4 of these. I started with D right here, and here's A, and here's B, and here is C. Now, that's still equal to 360 when all said and done. Sorry that it kind of slopes off right there. I'm going to combine some like terms. 10x, 24x, 32x, 37x, and I assume this will add ultimately. 13 minus 11 is 2, plus 7 is 9, plus 18 is 27. Okay. Subtract 27 from both sides. Let's hope this thing comes out cleanly, especially because I'm going to have to substitute. Find measures of angles B and C. 333. And that is clean. That should be 9, right? Because 10 is, yeah, that should be x equals 9. Okay, x equals 9, not the full answer here. I need to find the measure of angle B, and that'll be 8 times 9 plus 7, which is 63 plus 7. That is 70 degrees. No, not 63, 72. Oh, no. Oh, no. Oh, no. I've never done that before in my life. I was thinking 9 times 7. 72 plus 7 is 79 degrees. And then measure of angle C is 5 times 9 plus 18, which is 45 plus 18, which is 63 degrees right there. Okay, now notice that I put the degree symbols on these problems here, and I actually didn't on this one. That's because the x was a variable which has a degree symbol. This said solve for the measures of angles B and C, and you actually need degrees for those in the end. Okay, I'm going to go ahead and move down. Number 2, in a convex octagon, 3 of the exterior angles each have a measure of x degrees. The other 5 exterior angles have a measure of 2x plus 7 degrees. Find the measure of each exterior angle. Okay, I'm going to present to you an octagon, and it's going to be regular in shape, but I'm going to show you how much this does not matter for this. I'm really representing what it is here. Last time you saw that d equals 180 times n minus 2 stuff, right? But this is now referring to exterior angles, not interior angles. So exterior angles look like these ones right here. You extend a side outward, these kinds of things. So this, for example, this one could be your x degrees. Well, there are 3 of them. X degrees, x degrees, x degrees. And then all the other ones, the other 5 have 2x plus 7 degrees. Now, the important aspect of this is the interior angle sum of these, regular octagon or not, doesn't matter. The interior angle sum of an octagon is 180 times n minus 2, or 1080, I think, something like that. I don't know. But exterior angle sum of an octagon, of a triangle, of a dodecagon, of a 100gon, it's always the same, which is still 360. So I have 3 exterior angles with a measure of x. I have 5 exterior angles with a measure of 2x plus 7, and the sum of those exterior angles is 360. It does not matter that this was an octagon, except to tell you how many angles that there are. 3, 5, make 8. Otherwise, the sum is just that. So 10x plus 35. So now I'm just going to solve for x here. It says find the measure of each exterior angle, though, so we have to kind of work off that. So 13x, let's subtract and divide. 130 and then 90. I don't know if that divides evenly. I think 2. Oh, wait, no, hold on. Here, you know, I'll use a calculator. Give me 1 second. I don't want to mess this one up. I should. Okay, 25. Okay, 25. So x is 25. So one type of angle measure. It says of each exterior angle. So 3 of them, the x ones are going to be 25 degrees. And then the 2x plus 7 ones are going to be, so each. And then the 2x plus 7 ones are going to be 2 times 25 plus 7, which is 57 degrees each. Okay, so I hope that that works out with the way that I labeled them, because I was going to say one kind of angle and the other kind of angle, and I guess that works. Okay, number 3. The sum of the interior angles of a polygon is 3,960 degrees. How many sides does the polygon have? If we go based off this formula one more time here, well, I don't know how many times, but let's revisit this thing. D is 180 times n minus 2. This is the sum. This is the 3960 over here. We need to find out what n is based on this. Now, it's just an algebra thing. You could distribute 180, but you could also divide by 180 here. If it's not divisible by 180, something's wrong with the problem. And once again, I'll refer to the calculator, 3960 divided by 180. So I got 22. Now, that's not the number of sides. That is n minus 2. Technically, the number of triangles. So n is 24 sides. If you don't know what I mean by number of triangles, I drew it out really quickly on that one quadrilateral. Let me show you on this octagon right here as an example. How many triangles does an octagon have? If I go from one vertex here into all the non-adjacent sides of that vertex and draw diagonals, I can create triangles which are made up of the interior angles of the octagon like this. An 8-sided shape has that was not a marker, has 1, 2, 3, 4, 5, 6 triangles. There are always 2 less triangles than there are sides. Remember, the quadrilaterals, 4-sided shape had 2 triangles, 8-sided shape has 6 triangles, and a 24-sided shape has 22 triangles. All right, so it's always made up of that. The 180 is the part of the triangle interior angle sum. That's why the formula is what it is. All right, let's move forward. Let's solve for x at number 4. Once again, you're looking at a visual of exterior angles. Does not matter that it is a pentagon, 5-sided shape. The sum is still 360 degrees. So I'm going to start from here and work around the clock. I got 7x plus 4 degrees, and so on and so forth. Very similar to the last kind of problem with this. This one is... it just says solve for x, though. It doesn't say find the measure of each angle. So 12x, 16x, 25x, 29x. 4. Oh, hold on. Oh, okay, that's a 4. That's not a 4x. This is a 4 plus, just so you know. Give me 1 second. All right. 4, 8, 17, 11, 12. All right. 29x equals 348, and x equals, well, 290. It must be 12. And if it's not, I owe you something. I don't know what. All right, x equals 12. Nothing else to solve for after that. So once again, the sum is 360 for exterior angles, period. All right. If the exterior angle of a regular polygon is 22.5 degrees, how many sides does it have? So a regular polygon, I did one with the octagon thing, right? Just as another way of just drawing it again. This is a regular octagon. This is a regular decagon. This is a regular hexagon and a regular quadrilateral even. All sides equiangular, or the polygons equiangular and equilateral. All sides congruent, all angles congruent. So they're talking about another one that has something like this. So in a regular polygon, if all angles are congruent, we really talk about the interior angles with that, then so are the exterior angles. They're all congruent as well. So if I add one exterior angle with another, and they're all the same one this many times, I should get 360 degrees. But how many are there really? It says how many sides does it have. Let's say there are n of them. If I take my E, my exterior angle value, and I multiply by the number of sides, I should get 360. So, what I need to find out is, and my E, by the way, is 22.5. What I need to find out, by the way, is how many sides are there. So here's a setup. Now, normally you'd probably see, I'll show you after, but normally you'd probably see this expressed differently. I'm just giving you a buildup of that you can do. A lot of other ways you can do the problem with the interior angle stuff as well, but this should be significantly faster this way. I think that should be 16. So hold on, 360 divided by 22.5. Oh, I multiplied 360 divided by 22.5. 16. Okay, so n equals 16 sides. I was going to say that normally you might be more familiar with a formula saying that E is 360 over n, where E is the measure of each exterior angle, n is the number of sides. Well, this is all a rewrite of that, right? But you add n amounts of E's and you get that too. Okay, that is some of the polygon stuff. Let's move forward into some parallelogram stuff. Let's solve for x in parallelogram LMNP. Now, a parallelogram has it has a definition, opposite sides parallel, but it has a few properties as well. Among them, one of them is the opposite sides of any parallelogram are congruent. So, solve for x in LMNP. LM is congruent to Pn here. So, 9x minus 25 will equal 5x plus 7. And you're probably tuned, otherwise you're going like, how else do I solve other than setting these things equal? I get it, but you do kind of need to know the properties along the way as well. Okay, x is going to be 8 in that problem, as you see when you set them equal. Hopefully you can follow the algebra and trust my own algebra as well. Okay, letter B of this, given parallelogram NPQR, if NS is 2x plus 7, this guy, and SQ is 5x minus 23. Find NQ. Let me list off some of the properties. I don't know if we're going to run into them, and I just want to make sure that we do them. Parallelograms. Opposite sides parallel. Two pairs of them. Both pairs of opposite sides are congruent. Both pairs of opposite angles are congruent, like these guys. Any set of consecutive angles in a parallelogram are supplementary. They add to 180. And the diagonals bisect each other. So, the diagonals aren't congruent, but they bisect each other, so the parts are congruent. NS should be congruent to SQ. So I can set 2x plus 7 equal to 5x minus 23. I can subtract 2x from both sides, add 23 to both sides, and divide both sides by 3. I get x equals 10. They do ask us to find the length of NQ. Now, NQ is the entire diagonal. So you have options. You can substitute 10 into here and add them both. You could substitute x into one of them to represent half the diagonal. It is bisected, and you can double it. I'm going to go for that one. I'm going to say NQ is double that of NS, which is 2 times 2x plus 7, so 2 times 10 plus 7, or 2 27s, or 54. This is not degrees. This is the length of something. If you want to kind of confirm that, 5 times 10 is 50, minus 23 is also 27. 2 27s is 54. All right, that's the end of that page. That is number 6. Okay, in the parallelogram below, solve for u and v. Now, I did make mention of opposite angles congruent and consecutive angles supplementary. So you have some options on where you can go with this. Really, I mean, go with where you'd like to. Let's go with the equal ones to begin with first. 2u and 124. They should be equal to each other as they are opposite angles in this parallelogram, not x. Let's go to u, and that is 62. So u is 62. Now, you can substitute 62 in for u here, but you'll get 124. So now let's just work off this v right here, being a different one than this. These should add to 180. Remember, parallelogram, opposite sides parallel, would mean these are same side interior angles, 2 lines cut by a transversal. They should be supplementary. So let's go ahead and get that v. V minus 3 plus... Let's keep going. V plus 121 is 180. Subtract 180 from both sides. You get v is 59. Any questions? Okay, I'm moving forward. Number 8. Find the coordinates of the intersection of the diagonals of the parallelogram with the vertices -2, -1, 1, 3, 6, 3, and 3, -1. All right, find the coordinates of the intersection of the diagonals. We just learned or heard, once again, that diagonals bisect each other. Each diagonal meets at their respective midpoints. So when we find the coordinates of these diagonals, listen, I'm going to plot them on a graph. Wherever they intersect, but it might be a decimal, so we might have to play with that. We need their midpoints. We need the diagonals' midpoints. Now, here are the vertices that they give us, -2, -1. And by the way, they are concurrent at the same midpoint. -2, -1, 1, 3, 6, 3, and 3, -1. And this is a fine parallelogram, as you have a set of horizontal lines. That's always better to work off of. But we are referring to diagonals, so I don't know how much that's going to matter anyway. For other problems, I'd love to work off those parallelograms. Okay, I'm going to draw the diagonals kind of in like a dotted green line here. So going across there and going across there. Now, if you have a ruler and you draw the lines, or if you have the tool that I have, which doesn't snap perfectly, then you can probably surmise where these are meeting at, which looks like it's 2, 1. If we want a final answer already, 2, 1 is going to be it. However, let's look at this a little bit more in terms of what you can do graphically, what you can do mathematically, and all that good stuff to find one of these. Remember, you only need to find one of the midpoints. They're both the same midpoint. So let's go from like here to here, for example. One way of doing a midpoint is counting your slope from one point to the other and getting half of that. So for example, this goes down 1, 2, 3, 4, and right 1, 2, -4 over 2. Instead, if I go down 2 and over 1, boom, I hit that point as well. That's another way of discovering midpoint. So down 2 over 1 like that, which is at 2, 1 as a point. The other thing you could do, pick those points, 1, 3, and 3, -1 as x, y, and calculate those midpoints. So your midpoint would then be at average your x's, average your y's, like so. 1 plus 3 is 4. 4 divided by 2 you can see is 2. 3 plus -1 is 2. 2 divided by 2 you can see is 1. So we still get the answer. So that's how that stuff works. I'm showing you different variations of it, but if you're given the graph and you can draw straight lines with it, you can also find it just by looking at where they intersect, assuming they were integers, which those were. Okay, number 9. 3 vertices are given of parallelogram A, B, C, D. Find the coordinates of the remaining vertex given A and B and D. So we are missing C. And the letters here actually matter this time, not only the ones that they gave you, but the way that they wrote it. Cool, it's alphabetical. But let's look at what this is all about here. Let's start with the graph. And this time I'm only going to use the graph for working out this answer. Using the graph is actually very important for a concept of this answer. Now, if I give you an option of a region where C is, what would you say? Could you say, see, I could connect, if I connected A, B, and D like this, then C would be over here. However, if I connected A, B, and D like this, then C would be over here. understanding of parallelogram's nature. If I connected A, B, and D, let me undo. If I connected A, B, and D like this, then C would be somewhere over here. So which one is it? This is where because those are three different variations, this is where the letter order matters. Let me get B back. A, B, C, D. That means A needs to connect to B, B needs to connect C, C needs to connect to D, and D with A. So it's going to be this one over here, and maybe you see which one it is. So how do we work this out? Parallelograms have opposite sides parallel, so if you work the slopes off this thing, oh, I don't want the green dotted line. If you work the slopes off this thing, like opposite the one that would be connecting to a certain segment you're looking for, then you can find it. And there are different versions of that, so that's what we have so far. For example, from A to D is over 1, 2, 3, 4, and up 1, 2. So over 4, up 2. So from B to C should also be the same thing. Over 1, 2, 3, 4, and up 1, 2. Boom, that would be C right there. That was the harder one to do as far as counting a rise and run and such, but since I probably only have one of each problem, I wanted to show you that. However, you could have also gone from A to B is just down 2, so from D to C is just down 2. So what are the coordinates of C? 2, 0. 2, 0. Okay, let's move forward. Number 10. Find the coordinates of the intersection of the diagonals. Okay, it's the same thing as before, the coordinates of the intersection. Since you saw the midpoint one before, I'll just go straight into this one as it is, unless I need to calculate something a little more so because it's like a tweener. But here's Q. Here's R. S is 4, -3. And T is -6, -3. QRST. All right, got another parallelogram. Now, we don't need to confirm it is. If they give you the problem, we can just expect that it is. So hopefully you plot the points just fine here. Okay, so number 10. If I draw straight enough lines, looks like I'm hitting at that -2, -1. So before it was 2, 1, now it's at -2, -1. Now, without me calculating midpoint with averages, I want to remind you that in case your lines aren't straight, you can go from one to another. From R to T, you're going down 4 and left 8. So instead, go down 2 and left 4. Boom, you can hit that point. Go half the distance and you'll find it. There it is. Okay, another kind of question like number 9, I guess, is number 11. So the same thing as before. We have J, K, and L. We need to find M. It's a parallelogram written as J, K, L, M. So J to K to L need to connect in that way. So I got J as 1, 4, K as 5, 3, and L as 6, -3. J, K, L. And they do connect. I was like, what's the word? Correct? They do connect in that way, so we're going to find M in this other slot after we work out a slope. So check it out. For example, from K to J, opposite from L to M. From K to J, go up 1, left 1, 2, 3, 4. So from L to M, we can go up 1 over 1, 2, 3, 4 like that. And then we're going to have M like that at 2, -2. A lot of answers around 2s and 1s and things like that. That is the coordinates of vertex M. And you could confirm it using the other ones. Down 1, 2, 3, 4, 5, 6 over 1. Down 1, 2, 3, 4, 5, 6 over 1. So that works out. And there's your parallelogram. Okay, moving on. Still with parallelograms. Determine if the following is a parallelogram using the distance formula. So no graph provided. I'll show you a graph after to confirm that it worked out. But distance formula, what makes something a parallelogram with that? We need opposite sides to be equal. So I guess we're calling this thing parallelogram ABCD, or this is where it would be helpful to actually see the parallelogram for what it is. I'm going to assume that it's ABCD. So we want to find the length of AB. We want to find the length of CD. We want to then and show that they're equal. And then we want to find the length of AD, and BC. Again, this is where a drawing's kind of nice for A, B, C, D. We need to see that these two are congruent and these two are congruent. They say distance formula, so we want opposite sides congruent. That is the converse of the opposite sides theorem for parallelograms. Okay, distance formula itself. Square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. It's really, and you know, if I ever do it with my students, I do more on the graph. I do more Pythagorean theorem, or I could ask you the same questions as this stuff here and make sense of it. So for AB, and I think I'm just going to do it for AB, and then I'll probably go a little faster after this. So if my x2, x1 stuff, if I did it like that, I'd do 1 minus negative 7 squared plus, and then 2 minus 4 quantity squared. So 1 minus negative 7 is 1 plus 7, which is 8. And then 2 minus 4 is negative 2. So we have square root of 64 plus 4, which is square root of 68. Now square root of 68 reduces to 2, or simplifies to 2 root 17. I think at the point that you hit square root of 68, then you're probably pretty good to go as far as what it looks like for an answer. CD. Okay, here, I'll do it one more time. 1 minus 9 quantity squared, boom, boom, and then negative 6 minus negative 8 quantity squared. Like that. I gotta really punch this one in. So this is negative 8 quantity squared plus, and that's negative 6 plus 8, which is 2. 2 quantity squared. Remember, when you square a negative, it turns positive. So that is 64 plus 4 once again, which gets you to that thing, right? Root 68 and 2 root 17. So those are the same. Same length, opposite sides equal. That stuff works out. Now, if you don't know distance formula for what it is, once again, it's a rewrite of the Pythagorean theorem, and I'm going to be bringing that up a little bit more over time. It's kind of like if you do C. C is the square root of a squared plus b squared, meaning a and b are the sides of a triangle, right? A, b, the legs, the distance of the legs of the triangle. When I do my x2 minus x1, I'm finding the distance between my x's, and this is the distance between my y's. So what I'm going to do for AD and BC is I'm just going to ask you, what's the distance between this number and this number? And that's how I kind of want to work these other ones out. So I'm less work required. You can still subtract and figure it out. And when I write these distances, I'm just going to say them positive each time, because as you notice, squaring a negative number turns it positive anyway. So for AD, I need the distance between negative 7 and 1. Distance between my x's, that's 8. So I'm going to do 8 squared. And then I need the distance between 4 and negative 6, which is 10. Not 2, but 10. So that's 10 squared. So 64 plus 100, which is root 164. 4 and 41. So it's 2 root 41. Like so. And then on the length of BC, from B to C, from 1 to 9, that distance is 8. From 2 to negative 8, that distance is 10. And you can see what we're doing here once again. It's the same exact math. So those are the same as well. So that checks out. Therefore, yes, this is a parallelogram. And I didn't even realize, see, normally when we do ones out of the textbook, it's like, it is a parallelogram, just show it is. Determine if it is. Yes, it is. This is by the, I forget what they call it. Parallelogram opposite sides converse. Parallelogram. I think, wait, opposite sides congruent converse. I don't want to write it because I don't know what it is. Sorry. It's something like that. But basically, the converse of the opposite sides are congruent theorem. Okay, I didn't do a graph visual on that one. I'll do it. Yeah, let me do that really fast. I just need a graph thing for it. So let me kind of clip. I got to delete this for 1 second to clip something out, and then I'll put it back in. Of course, you already saw that part of the video, so I don't know if that matters. So let's, whoa. So I want to show you the graph visual of this guy here, in case you get to use it, in case you wanted to use it, and stuff like that. So for A, B, C, D, and again, we just completely trusted that that's how that thing worked, calling it A, B, C, D like that. So here would be A, here would be B, C is way over here, and D is way right there. So it still works. Big old parallelogram. The way that I would have just constructed this, distance formula is what it is. And listen, I think from here on out, I'll probably just use the distance formula, not a graph. But here's my support of what I was actually doing. The distance between, the AB part, right? The distance between the x's of 1 and -7, the distance is 8. How can you tell? 1, 2, 3, 4, 5, 6, 7, 8. And then it goes down to, that distance is 2 between the y's. This is a right triangle, folks. This right here. This is, Pythagorean theorem says I can do this with my right triangle. If I'm trying to find this length AB, here's 8, here's 2. So I'd say AB squared is, 8 squared plus x squared, plus 2 squared, I should say. And then, you take the square root of both sides as you work that stuff out. So that's what we're doing on those things, right? You can count slopes over 8 down 2. Honestly, once I get my over 8 down 2 for both, then I reckon it, because that's what I said on this one. I said, you're going to get the same answer. I don't know if at that stage you're allowed to just say, well, they're the same, or if they said find the actual lengths themselves. But the same thing here. This distance here is 10, and this distance here is 8, right? This distance here is down 10 over 8. So that's also getting you those lengths by doing those counts. If you have them on a graph, they did say distance formula though, so I'm just going to respect that for what it is. But that's what you do on graphs. I will, this time, if I have a distance formula thing to do, same with slope formula. x2 minus x1, y2 minus i1, the distances difference. So subtract them or know those distances. That's what I'm going to do here on out. Determine the following is a parallelogram using the slope formula for wxyz. Let's treat it for as it is. I'm going to assume it's parallelogram, wxyz. So for this here, I need to find the slope of, wxyz. Opposite sides need to be parallel. Boom, 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 boom. So I'm looking for same slope for wx and the same slope for yz. Then I need to find the same slope for wz. And it's not enough just to find one set. I need to find the set of the other. And then the slope for xy. I'll do it without a graph, although the graph I would have just counted how far up, how far over, things like that. But from w to x. Now remember, by the way, a slope is, if you're going to use the formula, I'll do it once, okay? I'll do it once. y2 minus y1 over x2 minus x1. I am using the slope formula right here. -6 plus 4 is -2. And then 1 plus 7 is 8. That's -1/4. Now this one, I'm going to not use the formula. I am using the formula, but I'm subtracting in my head. I'm doing distance from between y and z. From -12 to -13. Oh, here's where you got to be careful with this, though. The sign does matter now. From -12 to -13, I'm going down 1, if you want to say it that way. And from 1 to 5, I'm going right 4. Right? So the signs do matter here. I think it's one of those things where maybe you'd have to be careful here. But anyway, those two are the same. That's good. Now, does that mean these are parallel? It's not a guarantee. I'm guessing for the sake of this stuff, it's going to be, though. From w to z, we go from -12 to -4. That's a rise of 8. And from 1 to -7, that's a run of 8 to the left. So it's negative. That's a -1 slope. From x to y, from -13 to -6, it's a rise of 7, right? Is this going to be different? And from 5 to 1, oh, I want to look at this as a graph and see that this is right. And that's a run of that. I did everything right? 1 to -7 and all that stuff. It's -7/4. Okay, well, those weren't the same. Now I'm curious to see what this looks like on a graph. Give me my graph that I just copied from over here. Give me this. I'm actually curious because the whole test for this is whether or not this is true. I didn't expect that. I want to make sure, maybe I should have used my slope formula. I want to make sure I didn't make a mistake. Let's check it out. Let's check it out. W, let's just see the look. W, X, Y, oh, this is -13. This is going to go kind of low. But 5, -11, 12, 13. Okay, so this is why you probably can't use a graph. And Z is at 1, -12. kind of like that. You know what? That doesn't look like a parallelogram. I know I'm just going off of whatever, but it doesn't look like a parallelogram. Just because these opposite sides are parallel, and again, not to scale, but just because these opposite sides are parallel, don't mean these are. And Okay, it was good to show that. Is this a parallelogram? No. So, first time we're kind of doing a test of that way. So I just wanted the visual to make sure what I did was good. I think it was. I don't know if I plotted these very well, but there you have it. Is all that? Yeah. Yeah, okay. Where's my x to y? Okay. All right, let's move on. Determine whether it's a parallelogram using the slope and distance formula. Now, why would they make you do both? Well, there's another theorem that in a parallelogram, and this, we don't know it's a parallelogram, clearly, but in a parallelogram, if one pair of opposite sides is both congruent and parallel, then you do have a parallelogram. So this time, let's choose one set. Let's choose one set and work off of that one, see if they're both congruent and parallel off of that. So that's what I'm going to do. So for J, K, L, M, let's look at J with K, let's look at L with M, and go off that, okay? I'm not going to use the visual this time. I am going to just compute. So let's find the length of JK. Let's find the length of LM, and then let's find the slope of segment JK, and then let's find the slope of segment LM. Now, a lot of this is going to be based off the same numbers, but I have to be cautious of signs when I do my slopes. So from J to K, from -9 to 5 is -5 is 4. From -2 to 1 is 3. I already know that's going to be 5. Okay, so there's that length. Now listen, if one part of this breaks, like if the lengths aren't the same, you can stop. You can say no, and you can stop then and there. You're done. From 1 to -3 is 4. From -4 to -7 is 3. Okay, so this is also going to work out as well. That's 5, right? Same stuff. Okay, lengths are the same. That doesn't mean it's a parallelogram yet. Let's use the slopes of these things as well. From J to K, rise, let's go from 1 to -2. So that's a fall of 3. And then from -5 to -9, that's 4 over, so 3/4. Really what I'm looking for here is, are the signs the same? I still don't know. I have no idea. I didn't draw it. So for L to M, from -7 to -4, that's a rise of 3, literally. And from -3 to +1, that is a run of +4, so 3/4. So yes, this thing is a parallelogram. This is called the opposite sides parallel and congruent theorem. Opposite sides parallel and congruent theorem. I mean, it's in the name. And that's what we get. Okay, number 15. Let's find the values of x and y that make the quadrilateral a parallelogram. We're going back to our properties from before. In a parallelogram, opposite sides should be congruent. So to solve for x, I'm going to set 3x plus 15 equal to 19x minus 9. Subtract 13x from both sides. Add 9 to both sides. Divide both sides by 6. That's the value that would make it a parallelogram, but I still need to find y. These are not congruent, clearly not congruent. One's clearly obtuse, one's clearly acute. In case you were intending on setting them equal, don't. They add to make 180 degrees. They are supplementary. Like so. 14y minus 30 is 180. And 15. Yeah. Let's do that math. All right. There's a lot of space for me to write, so. All right, let's move forward. Number 16, which statement is true? All rectangles are squares? No. Here's a rectangle. Let me try and counter some of these if I'm able to do it fast enough. Here's a rectangle, it's not a square. All parallelograms are quadrilaterals? Absolutely. They're all four-sided shapes. If that's the only statement, we'll leave it, but I want to see what the other ones are. All quadrilaterals are parallelograms? No. Let me present to you. Not just a random one. Let me present to you something that we're not talking about here, a trapezoid. That's a quadrilateral that's not a parallelogram. It has one set of parallel sides parallel, but not both. All quadrilaterals are squares. No. You can clearly see different versions of them right there. Let me present to you a rhombus. I didn't realize I had that shape. I was spending so much time on another section on my 7-4 video trying to make a diamond by taking something. I didn't know I had that shape. Wow. Good to know in the future. Which statements are false? Oh, come on. Oh, is or are. Okay, so this is a tricky question. Which statement is true? Only one answer. Which statement is false? More than one, and you got to get the false ones. Okay. No square. Oh, geez. No squares are parallelograms. What did they just say? No squares are parallelograms. As if to say, any squares. I don't want to mess this up. Let's assume it's true and then see if that's incorrect. It's true that no squares, I don't know how to read this question, are parallelograms. Okay, all right, let's just talk about the math of it. All squares are parallelograms. Every square has opposite sides parallel. All squares are parallelograms is true. No squares are parallelograms should be false, so that is correctly false. I don't know why that was so hard to do. All rhombuses are rectangles. That is false, so we circle it. So, all rhombuses are rectangles. Listen, here's, now that I know where a rhombus tool is, here's a rhombus. Here's a rectangle. Not all rhombuses are rectangles. There is, however, a rhombus that is a rectangle when it's a square. Now, we haven't talked about rhombuses really yet, so let's talk about them. All sides congruent is a rhombus. All angles congruent, all angles right angles is a rectangle. A square is a quadrilateral or parallelogram with all angles congruent and all sides congruent, or all right angles and all of those. So it is a rhombus rectangle, both of them. So all rhombuses are rectangles, no, but false is correct. All squares are rectangles. All squares are rectangles. So it's false. We mark it wrong because that's true, right? I'm gonna put what's here. That's true, so it's wrong. All squares are rhombuses is also true, so we're gonna mark that wrong as well. So that's what I was kind of saying. All squares are rhombuses. All squares are rectangles. If you get tested on that, that is cruel. That first one, the no squares thing, I don't know why I had so much trouble with that. Double negative, you know. All right, finish the following statements. The diagonals of a parallelogram exist. The diagonals of a parallelogram bisect each other. I guess it's a properties-based thing. Okay, next one. A quadrilateral is a rhombus if and only if it has 4 congruent sides. So the if and only if statement says that any quadrilateral with 4 congruent sides is a rhombus, and any rhombus is a quadrilateral with 4 congruent sides. A quadrilateral is a rhombus if and only if its diagonals. Well, there are 2 things its diagonals can do, but it says a quadrilateral. So here's the thing. Rhombus's diagonals bisect their angles and they're perpendicular to each other. However, there's 1 of 2 things we can say. We can say either bisect their angles. I believe that's true if it's quadrilateral only, because this doesn't say parallelogram. It says quadrilateral. We could also, I believe, say are perpendicular bisectors of each other. I'm guessing it's the former that we're trying to do, because that's otherwise 2 statements, and then 1 is relying on it being a parallelogram. The second one is relying on it being a parallelogram, and I say that because the bisector part, this says quadrilateral there, so it's, I don't know. Sorry, not relying on it being a parallelogram, but relying on a parallelogram property for it to be true. See, parallelograms' diagonals don't bisect their angles, unless it's a rhombus. So I'm guessing it's more so this one, and I think that will be true once it's quadrilateral. It's not just the perpendicular one, though. I can make, we're not doing kites, but I can make a kite like this. The diagonals will be perpendicular if it was drawn perfectly. The diagonals would be perpendicular to each other in a kite. Okay, so like that. Anyway, so I just wanted to state that, really going for that top one. Okay, a quadrilateral is a rectangle if and only if it has 4 congruent sides. 4 right angles. I was thinking of a rhombus still. A quadrilateral is a square if and only if it is this is where we were talking about before. I'm guessing the first one's rhombus because it's less room, and a rectangle. A rhombus and a rectangle is a square. Now, I don't know how often we get to talk about these other things, but, all squares are rhombuses, all squares are rectangles, all rectangles are parallelograms, all rhombuses are parallelograms. Whatever a parallelogram's properties are, rhombuses and rectangles get, because they are a parallelogram that do this thing. A square takes on everything that a rectangle rhombus has, and therefore everything a parallelogram has. So if we get more into properties, we're going to have to be able to do that. A parallelogram is also a blank, blank, and a blank. I don't know if they're saying rectangle, rhombus, and square. If that's what they're going for, then that's technically not correct. I'm going to change the problem. I assume that's what they mean that they're trying to say. So I'm going to change it to a square. Because I was just kind of mentioning what that thing was here. So a square is also we just saw this. A quadrilateral is a square, but I want to just keep going with that. Rhombus, and it looks like this is what should fit. Parallelogram. A parallelogram is not a square. It can be a square, but when they say is, we assume always is, right? So, yeah, I'm going to go with that. A square is also a rhombus, rectangle, and parallelogram. Plus, it kind of went from parallelogram to rhombus to rectangle to square. I'm imagining this is what was intended to be written. So change it on yours if you have a packet with that. Number 19, if each quadrilateral below is a rectangle, find the missing measures. Okay, this is where knowing that a rectangle is also a parallelogram is helpful. Yes, a rectangle has this, and a rectangle, unlike a parallelogram, also has congruent diagonals, by the way. These would be the same length here. Not that they've asked about those yet. We'll see if they will. But a rectangle, just like a parallelogram, has opposite sides congruent. Those are the same. Those are the same. So when they're finding the length of VW, it's the same as YX. It's 31. WX is going to be the same as VY. That is 19. YW, and here's a diagonal. How do I find this length of YW? They didn't give us other lengths. Well, this is a right triangle. This is where, when I brought up Pythagorean theorem, this is where it actually pays off a little bit. A squared plus B squared equals C squared. I actually have to do some calculations here. So YW squared, let me do it the other way. 31 squared plus 19 squared is YW squared. I don't know 31 squared. I should. I think it's 961. So let me check that. 31 squared. 961. So 961 plus, I don't know, 19 squared. I think it's 361. 18 squared, I think it's 361. 361 is YW squared. 1322. And I don't know if that's a perfect square. It doesn't seem like one. Square root. No, it's not. So YW. Now listen. Square root of 1322. It's one of those things where I don't know if it has any perfect square factors. I'm going to leave it like that. They're not asking me to round, so I'm not going to round it. I'm just going to leave it like this. If you want to say what it's rounded to about, it's about 36.4 or 36.36. I'm going to get a little more precise. Around 36.36. ZX would be half of this. So here's the thing. And listen, I'm going to answer VX first. VX is the same as YW. This is also going to be root 1322, okay? Their diagonals are congruent in a rectangle. ZX would be half of VX. So root 1322 over 2, which I guess if I go off rounded, normally you don't use rounded answers for, you don't round early and then calculate, but this will still round to about 18.18. So there's that one, and that's the answer I'm going with. Assuming I didn't make any mistakes on my 19 squared. I don't think I did. That's just how it's set up. That's part A. Part B must be the next page. Okay, part B. That's a lot of numbers. Also a rectangle. The only thing you're given is 59. How do we do this? Well, here's the thing. A lot of the lengths are going to be the same, or measures are going to be the same. This is a right angle. That means that 59 degrees and measure of angle 11 are going to be complementary. So Measure of angle 11 plus 59 degrees is 90. Not 180, but 90. So measure of angle 11 is going to be 31 degrees. Now, we need degree symbols for all of these. Now, just another heads up on these things. I mean, we can work this a lot of different ways. Like, for instance, rectangles opposite sides parallel. So 11 and 4 would be alternate interior angles that are congruent. 4 would also be 31 degrees, like that. And then the other part that you start to recognize for this is these are also isosceles triangles. These are congruent to each other. These are congruent to each other. These are congruent. So it's really just the markings of these. So I'm just going to go ahead and give you what's what. 6 is 59 degrees. 1 is 59 degrees. 3 is 59 degrees. What is another? 31. So 4, I already got us 31. 5 is 31 degrees. And 2. Now we have these central angles. You can work off either set. Like, again, if this is 59 and this is 59, then 9 is, whatever adds to 180 with that. So the measure of angle 9 plus two 59-degree angles is 180. And that's 118. So measure of angle 9 is 62. 62 degrees. So 62 degrees. Then so would 8. 8 would be vertical angle with 9. So 62 degrees. 10 and 7 would be linear pairs with this. We already saw what the linear pair was. It's 118, right? So that's 118. And that should be those answers. Getting a little blue blind on that problem. I'm going to move forward. Another rectangle. Find the measure of angle GJK. Where's K? Oh, right here. Measure of angle GJK, given these angles 7x minus 16 and 5x plus 8. I did just mention on the other problem that you have a pair. Ignore our marking for now. I have a pair of two parallel lines cut by a transversal, which makes these alternate interior angles. These are congruent to each other. I can set these equal. They don't add to 180. I set them equal to each other. 5x plus 8 equal to 7x minus 16, and I can solve. 2x is 24 and x equals 12. So x is 12. Now, we need to find the measure of angle GJK. We can first find the measure of angle KJI. KJI, which is 7 times 12 minus 16. I would have preferred this one. 84 minus 16 is 68. So that's 68 degrees. So measure of angle GJK will be the complement of this one. So 90 minus 68, which is 22 degrees. That should be the answer. Because this is a rectangle, right? 90 degrees, all that kind of stuff, if you work it out. Okay, number 20. If JKLM is a rhombus, that means congruent sides here. That means diagonals are bisectors of each other and perpendicular. That means angles bisect each other. All this kind of stuff. I'll probably mark that stuff up later. But there's a rhombus. MK is 30. That's kind of hard to mark. So I'm going to put 15 and 15. I just mentioned the bisecting diagonals because it's a parallelogram. NL is 13. Where's N? Oh, if I can't find it, it's in the middle. NL is 13. That means this is 13, by the way. MKL is 41. So that's degrees. 41 degrees. Find each measure. Okay, NK, the length of NK, 15. So I already got that one because the bisected diagonals. JL is both 13s, so that's 26. KL, well, so here, KL, Pythagorean theorem is going to be used. Remember, diagonals are perpendicular to each other in a rhombus. So I have, once again, a right triangle with 15 and 13 and an unknown KL length there. So 15 squared plus 13 squared is KL squared. And I can't imagine that this is a Pythagorean triple, so you're going to also have another kind of random number here. 225 plus 169 is KL squared, which is... I can't do math in my head very well anymore. At least I can't do addition in my head very well anymore. 394. Yeah, this isn't going to be a perfect square. It's around 19 something. Really close to 20, really. It's almost 20. So root 394, but that's the side length. And all sides are congruent. So if they ask for any other side lengths, which they're not, then we would go off that. Okay, let me erase what's in there because the rest are angle measures. I want to just work off that. So I'll bring the 41 back here. Doesn't really look very rhombus-like. Oh, yeah, maybe it does. All right, measure of angle JKM. Well, if this one's 41 degrees, so is this. Angles are bisected by those diagonals. So 41 degrees. JML is this entire other side angle. Now, in a parallelogram, like a rhombus, opposite angles are congruent. So 2 41s is 82. So that's going to be 82 degrees. MLK should be supplementary to these ones. So 180 minus 82. And that'll be 98 degrees. Measure of angle MNL. MNL, that's one of the 90-degree angles right there, perpendicular. Measure of angle KJL would be half of the 98. 98 over 2, that's 49 degrees. Again, dividing that one by 2. Boop. Okay. That's number 20. Next page. Number 21, if PQRS is a rhombus, find angle PQR. Really measure of angle PQR, right? So PQR, the entire thing, a diagonal bisects its angle, so these two should be set equal to each other. We get 4x minus 27 equals 2x plus 7. Subtract 2x from both sides, add 27 to both sides, and divide both sides by 2. You get not 32, you get 17. I was going to subtract, you get 17. Find the measure of angle PQR. Just like the diagonal one, you can either substitute into both and add them together, or substitute into one and double it. So measure of angle PQR, I'm just going to go and double 2 times 17 plus 7. So let's double 34 plus 7, 41, and we get 82 degrees for the entire thing for PQR. All right, there's that one. Let's go to number 22. If WXYZ is a square with WZ is 27, find each measure. So this is 27. This is a square. A square, by definition, has the right... There are a bunch of properties. Listen, I could fill this thing up and mark it everywhere. I'm just going to start by definition. Right angles, all sides congruent. So ZY, like a rhombus itself and a square, is 27. WY is this length right here. So if these are both 27, let's go to Pythagorean theorem here. This is something you're going to learn later about what's called a 45-45-90 right triangle. It's a 1-to-1 to root 2 relationship. I'm going to give you this answer as accurately as I can. 27 squared, however, I don't know off the top of my head. I just lost it. I should do this here. 729? No. Yeah, 729. I didn't know that. Because that's also 9 cubed. That's why I was wondering. I need to add two 729s. Equals 729 plus 729. 1458. Now, if you take the square root here, I will simplify this for you. This is 2 root 27. Excuse me, 27 root 2. 27 root 2. Okay. So WY is 27 root 2. We're just going to leave it like that. RX is here. Now, it'll be half of 27 root 2. The diagonals are congruent to each other, and the diagonals bisect each other. So this is 27 root 2. That's half of 27 root 2. 27 root 2 all over 2. Measure angles here. Measure of angle WRZ. WRZ, 90 degrees. Like a rhombus would, a square is a rhombus, so that'll be 90 degrees here. XYZ. XYZ also 90 degrees, right angle as a square would, and ZWY. ZWY is this guy right here. Listen, a right angle is being bisected. 90 degrees is divided by 2, you get 45. There are 45s all throughout this thing. 90s and 45s. Those are the only angles that are going to exist in a square. And that's what that is. So, tricky problems with the Pythagorean theorem stuff, but we'll work it out like that. If you round, you round. I'll let you do that. All right, find the lengths of the diagonals of square w, x, y, z given this information. It's when in doubt, draw it out. Best to work this thing here. So w, x, y, z. It's a square. Diagonals will be congruent. I don't know if the diagonals are what we're given. They do say find the lengths of the diagonals, though. Let's see what we're given. We're given, this is why you want to draw it out. wy is 6x minus 7, that's one of the diagonals, and xz is 3x plus 2, that's the other diagonal. Okay, they'll be congruent. 6x minus 7 equals 3x plus 2. Subtract 3x, add 7, divide by 3. So that's x, not to confuse with this x, that's just a variable within here. So now to find the lengths of the diagonals, they're going to be the same. wy and xz will be the same. Let's substitute 3 into one of them, like 3x plus 2, which is 11. The length of each diagonal is 11. All right, end of that page. Number 24. Now, I inserted this graph stuff late in the game. I kind of want to use them, and then at the same time, I want to see what to do without them. Maybe. Given the vertices, determine the quadrilateral's most specific classification. So they only tell you it's a quadrilateral. They don't tell you whether it's even a parallelogram or not. So you really want to work off, depends. This is why I kind of want to draw it. If you knew it was a parallelogram, you'd really want to work off you can work off a couple things. The diagonals or any set of consecutive sides. Given that I don't know whether it's a parallelogram or not, I kind of want to just draw these ones. Because I know I inserted the drawings late. I'm going to work off the drawings for the sake of this. I'll tell you what you can test for these afterward, but I don't want to test for parallelogram and then later have to test for something else, if that makes sense. 3, -7. I'm assuming we're at least going to have parallelogram in a way, because otherwise we just got to call it quadrilateral, which isn't wrong if we do, but yeah. All right, so here's A, B, C, D. Now, if I were a betting man, I'd call this a rectangle. And here's the thing. Here's why visuals sometimes are like taboo in this thing. Clearly, it's not a square. Clearly, it's not a rhombus. We're not supposed to go by drawings, but clearly one is like more than double or almost triple the other one in length. But is it a parallelogram only, or is it also a rectangle? This is where we kind of have to do some test things. And this is why I want to do the drawing. As far as parallelogram goes, this has a rise from C to B as a rise of 3 and a run of 6. So the slope of segment CB is 1/2. And then from D to A, we can also confirm that it's a rise of 3 and a run of 6. So the slope of DA is also 1/2. Now from C to D, you go down 2, right 1. So the slope of CD is -2/1. And the slope of BA is also down to right 1. Now, with me going here, I confirm these are the same slope, these are the same slope, opposite sides parallel makes it a parallelogram. At the same time, I guess that works for me to do this. At the same time, these are also opposite reciprocal slopes. That means that this is also a rectangle. It says the most specific classification. This is a rectangle. Now, it's not a square because the sides aren't, not all sides congruent, which would be the next test. A rectangle with all sides congruent is a square. Did I show that? I did. Not from 1/2. Remember, 1/2 was 3/6. 3/6. Up 3/6. Pythagorean theorem, I'm not going to get the same length there as I would down 2/1 Pythagorean theorem. Those are different lengths, so it's not a square from that. What you could also do for a rectangle test is show that the diagonals are congruent, but you'd have to first make sure it's a parallelogram beforehand. That's why I'm going off the drawings, and I'm in the graph, and I'm intent on doing that for parallelogram's sake. Okay, QRST. I got -2, -7 for Q. R is 1, -5. S is 4, -7. and t is 1, -9. This is where the graph is going to be extremely helpful and actually make this a significantly easier question than the last one. If you have the drawing, and you can probably tell if you know enough about your numbers. These are both 1 for x. These are both -7 for y. But these are horizontally and vertically across from each other when you look at the diagonals of this thing. Because they call them quadrilaterals, we don't know their parallelograms, so let me confirm that here. Up 2 over 3, up 2 over 3, slope. And then, so same slope there. And then over here, down 2 over 3, and down 2 over 3. Now, if that didn't also tell you, it's a parallelogram, but if that didn't also tell you it's a rhombus, because they are 2, 3, 2, 3, it doesn't matter if they're positive or negative. If the leg lengths were 2 and 3, then the hypotenuses will all be square root of 13. These are all square root of 13 right here, if you use Pythagorean theorem. Therefore, this is a rhombus, all sides congruent. But let me go off the diagonals for a second. These diagonals, now that I know it's a parallelogram, these diagonals are vertical, unless I'd make a vertical line. They're vertical and horizontal. They're perpendicular to each other. In a parallelogram, if diagonals are perpendicular to each other, then you have a rhombus. Now, I didn't show very much work for this one. I demonstrated it. I believe, and I made this mention before, so I'm going to lay by my claim, if the diagonals are bisecting each other, which is actually what I could have done with the parallelogram part, right? If the diagonals bisect each other, length of 2 and 2, and 3 and 3, there's the 2/3 stuff. That's also where I could have done the slope. Next time, just do that, Mr. Robinson. Then you also have a rhombus because they're perpendicular bisectors. That's the reason I did perpendicular bisectors. I also showed the lengths here, but I didn't use Pythagorean theorem to you guys for it. All right, and the last one I have J, K, L, M. So 5, -1 for J. K is at 8, 2. L is at 11, 10. This is where the graph's a little less trusting. And M is at 8, 7. Might not be drawn to scale. I'm hoping it's at least a parallelogram. J, K, L, M. I'm saying it might not be a parallelogram. I think it is, though. Let's put it to the test. The slopes test. Oh, it probably is. My L, I don't know about my L, you know? I'm not going to look at the drawing and say definitively. Rise, run stuff. Right 3, up 3. The slope of segment JK is 1. M to L. That's 9, 10, 11, and then boom, boom, boom. So right 3, up 3. So had concern, no longer. Slope of ML. So those are the same, okay? Let's check these ones. From M to J. So from -1 to 7 is 8. And 1, 2, 3. So 8/3 from J to M. And then this one is from K to L. Let's kind of go this way. So 9, 10, 11. And then from 2 to 10 is 8. So that's a rise of 8, run of 3. We do have a parallelogram. Slope of KL is 8/3. All right, so we have a parallelogram there. Now, is it a rhombus, rectangle, or square? The sides are not congruent, either by appearance or by the 8 and 3 versus 3 and 3. They don't have opposite reciprocal slopes. That's not 1 and -1 or 8/3 and -3/8. So it's just a parallelogram. And it's not a square. It can't be a square if it's not a rhombus or rectangle. So just a parallelogram. We never had a square in any of those. Okay. All right, that is it for the main core problem set. You want to look at some Chapter 6 stuff. I'll go relatively quickly on these ones. Possible extra credit questions. Here we go. Graph and give the coordinates of the orthocenter of triangle BCD. Okay, an orthocenter is made by altitudes. I'm going to go fast on this stuff here now that it's been taught and stuff like that. But orthocenter is made from altitudes. For example, here's an altitude from C through BD. I know it's outside of it. And I can also do I'm going to do the altitude of, let's go through this one here. Let's find out what this slope is. Okay, this is a rise of 1 and run of 3. So I'm going to go from here, up 3, left 1, up 3, left 1, like this. Boom. And get that altitude that would have been perpendicular to BC like that. So this will be the orthocenter right there, which is negative 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. This is negative 7, 4. It's the orthocenter of that. Yeah, I'm going to work quickly on these ones. It's already been taught. It's a previous chapter stuff. Hopefully you can see the altitudes for what they are. Now, I did not do, by the way, I did not do this third altitude that would have looked kind of like that. I have no idea what the slope would have been, but because I didn't really track it. But there would have been another altitude for this one, in case you were like, that's the other one you found. Okay, graph and give the coordinates graphed, but give the coordinates of the circumcenter of triangle RST. Now, circumcenter is made from perpendicular bisectors. So you'd want to find midpoints of 2 of these guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Half of that is 1, 2, 3, 4, 5. Here's a midpoint of RS, perpendicular to a horizontal line, a vertical line. So the circumcenter is somewhere on that. Now let's find a midpoint of another. I'm going to do that half the distance thing. So 1, 2. I wish they had numbers. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so this is down 12 over 6. So half of 6 is 1, 2, 3, and half of that is up 6, and we get that point as well. Now, that was a slope. Hold on. That slope of ST was down 12 and left 6, which is positive 2. So the opposite reciprocal slope of that will be negative 1/2. So from here, I can go up 1, left 2 like that. Boom. You have to go perpendicular to it. It's not a median that we're going to draw. It's a perpendicular bisector. So like that. Perpendicular bisectors, we see our circumcenter there at negative 2, 0. This guy. Negative 2, 0. Okay. If Z is the in-center, find measure of angle ZTV. Well, an in-center is made from angle bisectors here. So everything is angle bisector. These are congruent here. These are congruent here, stuff like that. They need the measure of angle ZTV, this one over here eventually. It's going to take a little bit. Here's what we're going to do. Angle bisector means these two things are equal here. Like, for instance, this is 21, so is this, 21 degrees, which the important thing for us is going to be the whole thing is 42. That's going to be important. Let's find out this angle measure as well, the whole thing, by solving for x. And then 42 plus this whole thing's 180. And then we'll divide that angle by 2. So let's start with 5x plus 1 equals 8x minus 14. Subtract 3x, add 14, divide both sides by 3. And then just the whole thing. Let's do 5 times 5 plus 1 and double it for the whole thing, which is going to be doubling 26, which is 52 degrees. So this whole thing here is 52 degrees. So now we know that we have a 52 degree angle plus a 42 degree angle plus the measure of angle UTV is 180. So that's 94. And measure of angle UTV would then be 86. So that's not ZTV though. ZTV should be half of that. So measure of angle ZTV is half of 86, which is 43 degrees. There's the answer. All right, solve for x in this next guy here. It looks like we have a mid-center because you can see a mid-segment made by the midpoints. Segment made by midpoints here. What are they pointing at? Oh, these are angles. Okay, so and this is maybe tricky, but a mid-segment is not only half the length of that third side, but it's also parallel to it. The parallel part's important because parallel means these are same side interior angles. These are supplementary to each other. These add to 180. 8x minus 3 plus 16x minus 33 is 180. So 24x minus 36 is 180. They just said solve for x, so we'll just keep going. 216 and x equals 9. So x is 9. I'll move myself and scroll down. Here we go. Classify point C. Last 2 questions, I think. Classify point C. This is made from perpendicular bisectors. That'll be a circumcenter. An incenter is made from angle bisectors. Centroid is made from medians. And orthocenter is made from altitudes. This is a circumcenter. I see perpendicular lines at bisectors. It is A. And then last, classify point C. Point C is made by the medians. You can tell, well, yeah, by the medians, you can tell from vertex to midpoint right there. Medians give you a centroid. That is C. That's it. All right, guys, that ought to do it for... Whoop, sorry. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I'm going to put timestamps and all that stuff. Hopefully you already checked them out, or you can go back and revisit those. I'll give you this PDF and all. Take care. I will see you in the next one. I hope you are ready.